Welcome all. Good morning. Welcome to the second day of the Faculty Development Program on Fussy Mathematics and its Applications, organized by Department of Mathematics, Government College Daman in association with IQAC. Joining us today are Dr. S. Balasubramaniam, IQAC Coordinator and our Vice Principal, Dr.A.Sathya, Assistant Professor, Department of Mathematics, and the Convener and Organizing Secretary of this Faculty Development Program. Also joining us is Dr. K.Ganesan, Professor, Department of Mathematics, SRM Institute of Science and Technology, Chennai. I welcome all of you to the gathering. To begin with the proceedings, I request our dynamic IQAC Coordinator and Vice Principal, Dr. S. Balasubramanian, to give the welcome address.
Thank you, Dr. Vrinda. Welcome one and all, and a special welcome to the speaker of the day, Dr. Ganesan, from SRM Institute of Science and Technology, Chennai. Participants, you would have enjoyed and enriched regarding the fuzzy mathematics yesterday. Today also, I hope that everyone would be enjoying and enriching your knowledge regarding fuzzy mathematics. And we have a very resourceful resource person today, Dr. Ganesan. I welcome Dr. Ganesan on behalf of Government College Daman for this program, second day of the Faculty Development Program, and welcome all the participants. Thank you.
Vrinda madam, please unmute your mic.
Sorry for the technical glitch. Moving on to the introduction of the resource person. As already mentioned, Dr. K. Ganesan is a professor of mathematics at the SRM Institute of Science and Technology. His areas of specialization include fuzzy optimization, operations research, interval analysis, and ordinary and partial differential. Sir has over 40 publications in reputed research journals. He has attended around 10 international conferences and presented papers at them. And there are around 35 national conferences where he has presented papers. He has organized around 7 conferences, seminars, workshops, and has been a resource person at numerous workshops, faculty seminars, and the like. Sir has 2 research projects to his credit and is the co-author of 11 books and 3 edited volumes. And most of these books are textbooks for engineering students, management students, as well as students of science. Sir has over 30 years of teaching experience, and he has been a life member of several organizations like the Kerala Mathematical Association, the Indian Science Congress Association, etc. I'm very glad that Sir has accepted our invitation and has agreed to be a resource person at our faculty development program. It is a privilege to listen to you and learn from you, Sir. Now, I request Dr. K. Ganesan to begin his session on optimization problems under uncertain environment. Over to you, Sir.
A warm welcome and very good morning to one and all for attending this faculty development programming. First, let me thank the organizers for this FDP, the convener and the organizing secretary, Dr. Sathya, Vice Principal and IQAC Coordinator, Dr. Balasubramanian, the Principal, Dr. S. Kumar, Dr. Vrinda, and other organizing persons to give me an opportunity to interact with all my fellow colleagues, students through this online lecture. My today's lecture title is Optimization Problems Under Uncertain Environment. I really am very much thankful to Dr. Vrinda for her nice words on me. The outline of my talk will be, or includes, introduction to optimization, optimization under uncertainty, optimization in fuzzy environment, fuzzy modeling and fuzzy optimization, basic concepts, fuzzy linear programming, numerical example, conclusion, and some of the references. Introduction. Optimization is an important tool in making decisions and in analyzing physical systems. In mathematical terms, an optimization problem is the problem of finding the best solution from among the set of all feasible solutions. The first step in the optimization process is constructing an appropriate model. Modeling is the process of identifying and expressing in mathematical terms the objective, the variables, and the constraints of the problem. An objective is a quantitative measure of the performance of the system that we want to minimize or maximize. In manufacturing industries, we may want to maximize the profits, or we may want to minimize the cost of production, or we may want to maximize the number of products, whereas in fitting experimental data to a model, we may want to minimize the total deviation of the observed data from the predicted data. The variables or the unknowns are the components of the system for which we want to find values. In manufacturing, the variables may be the amount of each resource consumed, or the time spent on each activity, whereas in data fitting, the variables would be the parameters of the model. The constraints are the functions that describe the relationship among the variables and that define the allowable values for the variables. In manufacturing, the amount of a resource consumed cannot exceed the available amount because we cannot use more than the availability. The next step is determining the problem type. It is very much important that what type of problem is in front of us. An important step in the optimization process is classifying the optimization model. Since algorithms for solving such optimization problems are tailored to a particular type of problem. Continuous optimization. Models with the continuous variables are continuous optimization problems. For example, finding the extremal of a functional, finding the minimum or maximum of a continuous function, which comes under continuous optimization. Discrete optimization. Some models only make sense if the variables take on values from a discrete set, often a subset of integers. Models with the discrete variables are discrete optimization. For example, the integer programming problems, transportation problems, assignment problems, etc. Unconstrained optimization. Unconstrained optimization problems arise directly in many practical applications. They also arise in the reformulation of constrained optimization problems in which the constraints are replaced by a penalty term in the objective function. That means we have to optimize certain thing subject to no conditions. Without any restrictions or conditions, we have to optimize the certain things. That comes under unconstrained optimization. The next is constrained optimization. Constrained optimization problems arise from applications in which there are explicit constraints on the variables. The constraints on the variables can vary widely from simple bounds to a system of equalities and inequalities that model complex relationship among the variables. Constrained optimization problems can be further classified according to the nature of the constraints. Constraints that may be linear or nonlinear or convex, and the smoothness of the functions, whether the function is differentiable or non-differentiable. Most of the optimization problems have a single objective function. However, there are interesting cases when optimization problems have no objective function or multiple objective functions. Feasibility problems are the problems in which the goal is to find values for the variables that satisfy the constraints of a model with no particular objective to optimize. Complementarity problems are pervasive in engineering and economics. The goal is to find a solution that satisfies the complementarity conditions. Multi-objective optimization problems arise in many fields, such as engineering, economics, and logistics. When balance need to be taken in the presence of trade-offs between two or more conflicting objectives. For example, when developing a new component, it might involve minimizing the weight while maximizing the strength, or choosing a portfolio might involve maximizing the expected return while minimizing the risk. In practice, problems with multiple objectives often are reformulated as single objective problems by either forming a weighted combination of the different objectives or by replacing some of the objectives by constraints. Deterministic optimization versus stochastic optimization. In deterministic optimization, it is assumed that the data for the given problem are known accurately, precisely. But in the real world problems, the data cannot be known accurately for a variety of reasons. The first reason is due to simple measurement error. It is not exact data, or it involves more information cost due to lack of information or impreciseness, and hence the classical mathematical tools are insufficient to tackle such situations. When the values of variables cannot be precisely specified, they are said to be uncertain. If the values are uncertain, probability distributions may be used to quantify them. Alternatively, if they are best described by qualitative adjectives such as dry or wet, hot, cold, clean, or dry, fuzzy membership functions can be used to quantify them. So, both the probability distributions and the fuzzy membership functions of these uncertain or qualitative variables can be included in quantitative optimization models. Now, optimization under uncertainty. In the optimization problems, if the uncertain parameters are modeled by probability distributions, then it is a stochastic optimization. Stochastic optimization models take advantage of the fact that probability distributions governing the data are known or can be estimated. The goal is to find some policy that is feasible for all the possible data instances and optimizes the expected performance of the model. In the optimization problems, if the uncertain parameters are modeled by fuzzy numbers, then it is a fuzzy optimization. Fuzzy optimization is a well-known optimization problem in artificial intelligence, manufacturing management. So establishing a general and operable fuzzy optimization models are important in both the theory and applications. We restrict our talk to fuzzy optimization problems. Optimization in fuzzy environment. Just to see an example. Consider the problem of finding the maximum value of x given that x cannot exceed 11. It can be modeled as a linear programming problem as maximize x subject to the condition that x should not exceed 11, that is x is less than or equal to 1. And certainly the optimal solution will be x is equal to 11. Just on seeing this diagram, it's very easy to calculate it. It's a eclipse. The point of intersection for the line u is equal to x and x is equal to 11. That point gives the optimum solution, which x is equal to 11. On the other hand, suppose the objective is to obtain a value of x substantially larger than 10, while making sure that the maximum value of x should be in the neighborhood of 11 or in the region near 11, etc. This is no longer a eclipse optimization problem, whether it is a fuzzy optimization problem, just on seeing the diagram. Now, for any optimization problem, the physical problems are available only in terms of data. The problems may not be available in terms of mathematical equations. We should realize the nature of the problem, nature of the data is available. And then the first phase of any optimization problem is to find its mathematical model. Here, understanding the problem, first thing, in this stage, the stage constraints and goals of the system, as well as the relationship among them are understood clearly and expressed by sets. Fuzziness analysis, where the concept of fuzziness comes into this picture. On the basis of understanding of the background of the problem, information such as which kind of fuzzy data or elements is involved and what the position it takes, as well as the way in which it is expressed, should be analyzed and summarized. In this stage, the fuzzy information is usually expressed in a semantic way. Description and formulation of the fuzzy information. On the basis of the above steps, the fuzzy information, including ambiguity and vagueness, has been distinguished. What remains to do is to quantify the information in terms of appropriate tools and theory using fuzzy mathematics. In light of the nature and the ways of fuzzy information is expressed, a membership function can be selected to formulate it. The membership function is subjectively determined and preference based, which reflects the decision maker's preference on the objects. It usually applies to the situations involving the human factor with all its vagueness of perception, subjectivity, goals, and conception. Example, fuzzy goals with aspiration, fuzzy constraints with a tolerance. Such goals and constraints are expressed vaguely without sharp and thresholds to give the necessary flexibility and elasticity. The membership function may take a linear form or a nonlinear form, reflect the decision maker's preference and understanding of the problem. These sub-stages takes care of the transition from fuzzy modeling to the fuzzy optimization. Then development of the fuzzy model. Based upon the above stages, an appropriate fuzzy optimization model will be built by adopting some mathematical tools, catering for the characteristics of the problem. The optimization model may take the form of a fuzzy linear programming, or fuzzy nonlinear programming, or fuzzy dynamic programming, fuzzy multi-objective programming, or fuzzy possibilities linear programming, or convex programming. It may be anything. But again, we restrict our talk here itself to fuzzy linear programming problems, which is the very easier thing in the case of fuzzy optimization. Now, let us recall certain basic concepts, properties, results, which will be highly useful in developing the fuzzy linear programming models and finding their solutions. As we are talking about fuzzy linear programming problems, we recall all the concepts from the fuzzy sets which was introduced by Professor Zade in 1965. As all aware, the basic definitions for fuzzy set. Informally speaking, the sets which has no precise boundary. Fuzzy sets, the sets which has no precise boundaries. As I believe that the audience are faculty members and research scholars or postgraduate students, right? There is no need of getting into the classical sets in detail. Even the fuzzy sets notions, the basic concepts may also be well known to all of us. Anyway, let us start with the fuzzy number. A fuzzy set A tilde defined on the set of real numbers R is said to be a fuzzy number if its membership function is convex, normal, and piecewise continuous. I believe that all of us know the meaning of convex, normal, piecewise continuous. A fuzzy number A tilde, is said to be a triangular fuzzy number if its membership function is given by A tilde of X is represented by the straight line X minus A1 by A1 minus A2 within this interval A1, A2, and A3 minus X upon A3 minus A2 for the interval A2, A3. Whenever X is equal to A2, the membership grade is 1. You can substitute in either of these. As X is equal to A2, you will get the value 1. And the triangular fuzzy number can be denoted by a triplet. A tilde is equal to A1, A2, A3. A fuzzy number A tilde can also be is said to be a trapezoidal fuzzy number if its numbership function is of the form mu tilde A of x is equal to that values that is represented trapezoidal. Suppose we have the a graphical representation, you will see a trapezoidal for this, and the previous one you will see a triangle. Representing a trapezoidal fuzzy number in other way. Instead of representing as a four tuple as A1, A2, A3, A4, it can also be represented as A2, A3, H, K, where A2, A3, the interval A2, A3 we used to say as a core. That means the interval A1, A2, A3, those consist of those elements whose numbership grades are exactly 1. And H, the left side spread A2 minus A1, which we take it as H. Similarly, the right spread A4 minus A3, we take it as K. When the right spread as well as the left spread are same, that is when H is equal to K, we call the trapezoidal fuzzy number as a symmetric trapezoidal fuzzy number, and is denoted by A3, A tilde is equal to A2, A3, that means the core, and then left spread and the right spread, both are same. When A2 is equal to A3, then the trapezoidal fuzzy number A tilde is equal to A1, A2, A3, A4, which is nothing but a triangular fuzzy number, because when A2 is equal to A3, the core, the interval A2, A3 will be a single point A2. It becomes a triangular fuzzy number. Again, when H is equal to K, the triangular fuzzy number A tilde represented by A2, H, K become a symmetric triangular fuzzy number and is denoted by A2, H. Again, let us go to the trapezoidal fuzzy number. When we assume H is equal to K is equal to 0, that means the left spread as well as the right spread are 0, then what will happen to that trapezoidal fuzzy number A1, A2, A3, A4? It becomes an interval number or simply interval A2, A3, whose numbership function is defined in this way. For all x which are in the interval, it takes the numbership grade as 1, 0 otherwise. Again, if you assume that when H is equal to K is equal to 0 and A2 is equal to A3 are simply the trapezoidal number, if A1 is equal to A2 is equal to A3 is equal to A4, which is equivalent to a number A, then the trapezoidal fuzzy number A tilde A1, A2, A3, A4 becomes a Cripps number A tilde is equal to A. So, from these deductions, it is easy to see that by proper assumption, a trapezoidal fuzzy number can be reduced to a triangular fuzzy number. A triangular fuzzy number can be reduced to an interval number. An interval number can be reduced to a Cripps number. So, Every Cripps number is a subset of an interval. Every interval will be a subset of every triangular fuzzy number, every trapezoidal fuzzy number. And all the triangular fuzzy numbers are subset of trapezoidal fuzzy numbers. Now, let us because while studying about the fuzzy numbers, it is important to see what is meant by an alpha ket and a strong alpha ket. Alpha ket of a fuzzy number, for each alpha belongs to the interval 0, 1. An alpha ket is defined as the set of all x belongs to R whose membership grades are greater than or equal to alpha. Similarly, the set of all x belongs to R whose membership grades are strictly greater than alpha, we call as the strong alpha ket of the fuzzy number A till D. And it is evident that whatever be the fuzzy number, it may be of trapezoidal type or triangular type or any other Gaussian type, whatever it may be, even orthogonal fuzzy numbers, whatever it may be. The alpha ket of any fuzzy number will be a closed and bounded interval. Though initially there was no relations between the fuzzy mathematics and the interval mathematics, then when days go on, there is a very good relationship between, because every fuzzy number can be represented by its alpha ket, that means in terms of intervals. So while want to making arithmetic operations on fuzzy numbers, the scientists thought that why not we make the arithmetic operations on the alpha ket of the fuzzy numbers, that is on interval numbers, instead of making the arithmetic operations directly on the fuzzy numbers. Now, let us see the arithmetic operations, the standard arithmetic operations on interval numbers. And as you all aware that an interval is the set of all elements x belonging to R such that A1 is less than or equal to x is less than or equal to A2, which we denote it as an interval A1, A2. It's a known fact. Now, suppose we have two intervals A till day and B till day, and we define the arithmetic operations on that, the standard interval arithmetic, while adding two interval numbers A1, A2 plus B1, B2, just adding the corresponding components A1 plus B1, A2 plus B2. Whereas while subtracting A1, A2 minus B1, B2, which is equal to A1 minus B2, A2 minus B1, but it is not A1 minus B1, A2 minus B1, because it is not A1 minus B1, A2 minus B2, because the interval, there is a condition. When we say A1, A2 is an interval, A1 should always be less than or equal to A2. But if you define the subtraction operation component wise, that is as A1 minus B1, A2 minus B2, then this inequality may not be satisfied. A1 minus B1 may not be less than or equal to A2 minus B2. That's why they have defined in the other way. Then we can go for multiplication of two intervals A1, A2, B1, B2, and actually we do not know whether A1, A2, B1, B2 are negative or non-negative or positive. That we do not know. They are real numbers. That's all. A1, A2, B1, B2 are all real numbers. Their product is defined as another interval, alpha, beta, where alpha is nothing but minimum of all the combinations of the elements of A tilde and B tilde. That means the product of A1B1, A1B2, A2B1, A2B2. The minimum is a lower limit and the maximum is the upper limit. Then for the division, similarly, as in the case of multiplication, it can be defined, but with the condition that 0 should not be inside that interval B. That means 0 should not belong to the denominator interval. Now, based on this, the similar way, arithmetic operations on triangular fuzzy numbers can also be defined almost a similar way as we have done in the case of interval numbers. Only thing that A2 and B2, the other things are the minimum and the maximum. Divisions also there. Okay. Now, it is important to note that it's very, very important. Note that under this standard arithmetic operations, either on interval numbers or on fuzzy numbers of triangular type or trapezoidal type, whatever it may be, the multiplication of two triangular fuzzy numbers need not be a triangular fuzzy number. This is true. Similarly, when dividing a triangular fuzzy number by another triangular fuzzy number, the resulting may not be a triangular fuzzy number. And moreover, the fuzzy arithmetic does not satisfy the distributive law, which is very, very important for further development for any type of theoretical aspects. Now, I think now let us, as we are restricted ourselves to linear programming problems, and for simplicity, let us see certain aspects on the arithmetic operations of symmetric trapezoidal fuzzy numbers and their properties. This we have seen already, symmetric trapezoidal fuzzy number, and we have defined the arithmetic operations. This is actually myself and Professor Veeramani of IIT Madras during 2006, we have developed this arithmetic operations on symmetric trapezoidal fuzzy numbers, and our paper was published in Annals of Operations Research in 2006. Let us consider two symmetric trapezoidal fuzzy numbers, A1, A2, H, H, B1, B2, K, K, and subtraction, addition, multiplication. Okay. Or division, somewhere it is missed anyway. We will recall it. Division as well as scalar multiplication, all are available. I'll tell you the reason behind why we are defining, why we are altering the standard fuzzy arithmetic operations into this form. There is a purpose for reformulating the arithmetic operations that I will tell you while explaining the example. Okay, now ranking, it is very simple. Wherever we go for optimizing, or whenever we discuss with optimization problems, our optimization or our objective should either to maximize the profit or to minimize the cost. So we need a comparison. Without comparison, you cannot find the best one. So comparison of fuzzy numbers is very, very important while dealing with fuzzy optimization problems. Is it possible to compare any two fuzzy numbers? Or the fuzzy numbers are linearly ordered or at least partially ordered? For this purpose, we cannot compare it. The fuzzy numbers in general are not linearly ordered. In some cases, even it is not partially ordered. So they can be compared by using some other tools we call as the ranking function. We form a ranking function from the set of all fuzzy numbers to a set of real numbers. That means for every fuzzy number, we associate a real number. For every fuzzy number, we can associate with a real number. That is attained by using this type of formulas we call as fuzzy ranking functions. This we have used it. And using that ranking function, we can say when a fuzzy number is positive, when a fuzzy number is 0, when a fuzzy number is negative, all this, because otherwise if you are unable to compare the fuzzy numbers, then it is not easy to say a fuzzy number is 0 or a fuzzy number is positive or a fuzzy number is negative. Okay, right. Now, based on the above reformulated arithmetic operations on symmetric trapezoidal fuzzy numbers and the ranking function we have seen, we have proved one proposition and the theorem. They are very much useful in developing theory for the linear programming problems. For any, the proposition states that for any symmetric trapezoidal fuzzy numbers, A tilde, B tilde, and C tilde, we have the distributive law. You can verify by having any three triangular or trapezoidal fuzzy numbers, A tilde, B tilde, C tilde, and applying them in the standard fuzzy arithmetic, see that whether the distributive law is true or not. It won't be satisfied. The reason why I want to that the distributive law should be satisfied is, I'll tell you while explaining the example. Then the relation less than or equal to in the fuzzy sense is a partial order relation on the set of symmetric trapezoidal fuzzy numbers, as well as it is a linear order that we have proved. Okay. Now, this I have told you then. When we say that it is a positive trapezoidal fuzzy number, when we say that it is a negative, when we say that it is negative, positive, and equivalent 0, there are two things, One we call as equal to 0, and the other is equivalent to 0. This is because of the ranking function. Now, let us go to the general form of fuzzy linear programming problems. And we know this is this is general model in the case of classical linear programming problems also. Only thing we have used the inequality symbols as the inequality symbols in the fuzzy sense, and similarly instead of equal to we use equivalent. And we use in this problem Aij belongs to R, the set of real numbers. That means we have assumed in this problem the coefficient matrix, the components of the coefficient matrix are cribs, but it can be assumed as fuzzy numbers also. In the usual way, we can define the fuzzy feasible solution for a fuzzy linear programming problem and fuzzy optimum solution for a fuzzy linear programming problem. In the usual way, a fuzzy linear program can be expressed in its standard form as maximize Z tilde is equivalent to C tilde X tilde subject to A X tilde is equivalent to B tilde and X tilde is greater than or equal to 0 tilde. Here the bold letters denotes the vector, the fuzzy vector X tilde, the bold, it is a n component vector. Similarly, B, n component vector. C again n component vector, whereas A is a m by n Cripps matrix. In the usually how to find the basic feasible solution for a fuzzy linear programming problem. Then here is the problem, once we have the fuzzy linear programming problem, once the problem is available, then we have to look for a method or a procedure for finding the solution of that problem. For example, suppose we consider the fuzzy linear programming problems. We know in the literature there are different methods available in case of classical linear programming problems. Software is available. Whatever be the size of the problem, you can input the parameters in the system, in the program, certainly you will get the solution. Suppose you would like to apply the simplex method for solving a linear programming problem, the method is already available, the softwares are available. But whether the available algorithm, whether the available method, whether the available formulae can accommodate the fuzzy numbers, they will not. You cannot substitute a quantity which is nearer to 10 to any formula. You cannot. So we want all the imprices data expressed in terms of fuzzy numbers and then producing the suitable solution. And we know the procedure for a simplex method. The simplex method gives different steps, all from standard theorems. Just not like that. How to find the basis, how to find the basic feasible solution, how to improve further, when to stop, what is the indication that the problem poses an unbounded solution, what is the indication that the problem poses an optimal solution. All these things, all are provided by theorems. Are we capable of proving such theorems by using fuzzy numbers? Because, as we say that, the product of two triangular fuzzy numbers may not be a triangular fuzzy number. And the fuzzy arithmetic does not satisfy the distributive law. You cannot provide such a simplex algorithm which accepts the data as fuzzy numbers. It is not possible. That's why from the beginning itself, what the researchers are doing, after formulating the problem as a fuzzy linear programming problem or fuzzy nonlinear programming problem, single objective or multi-objective, anything it may be, they try to convert to a number of Cripps problems by using the concept of ranking function. They convert to a number of Cripps problems. Once the Cripps problems are available, then the methods are readily available for providing the solution. But finally, for the given fuzzy problem, you will get only the Cripps solution. And we ask ourselves, when our inputs are all fuzzy numbers, how can we expect that output is a Cripps number? It is not possible. It should not be. When our all parameters, the inputs are all fuzzy numbers, our output should also be a fuzzy number. We should develop a model, a method to provide such solutions. For that purpose, we have modified the arithmetic operations in such a way so that we can capable of proving the required theorems to develop a simplex method in fuzzy version. And all these conditions are, we have proved all the theorems, and as published in Annals of Operations Research in 2006. Here is that example. As I said, the physical problems may not be available in terms of mathematical equations. It may be differential equations, system of equations, linear or nonlinear equations, or mathematical programming of linear or nonlinear, whatever it may be. You only have data regarding the problem. Even you may not have the entire data. The data may be partial. By using all those available in-process data, we should formulate the problem. Just go through this. And the first phase of any problem solving is the important space is the mathematical formulation. Simply on reading it once, twice, thrice, you can easily understand. You can identify the objective of the problem. Then you can identify the resources and its availability. As you know, you cannot use more than the availability. The symbols, the inequalities which we had, and formulate this as a fuzzy linear programming problem of this maximize z is equivalent to this subject to 1, 2, 3 constraints and the non-negative restrictions x1 tilde, x2 tilde, x3 tilde are restricted to assign non-negative values because this x1, x2, x3 as the number of products of the types of P1, P2, P3 are to be manufactured. If at all you manufacture, you will have some non-negative. It won't be negative. The number of products will not be negative. That's why we impose the non-negative restrictions x1, x2, x3 are greater than or equal to 0 by applying the above theorems and the simplex method developed by using the theorems. We have obtained the solution without converting to classical form. Our inputs are fuzzy, our output is also fuzzy, and this is optimal solution by applying the simplex algorithm. This is because this method can be applied not only for linear programming problems, not only for single objective linear programming problems. It can be applied for multi-objective linear programming problems and the special cases of linear programming problems like transportation, assignment, traveling salesman, and non-linear programming problems, all these things. Also, the others, again, there is another way of representing the fuzzy numbers, which we call as the parametric form of fuzzy numbers. Okay. This Mingma and Candle, I think during 1990, they have proposed a type of definition for this parametric form. A triangular fuzzy number A tilde can also be expressed as the ordered pair A lower bar, A upper bar of functions, which satisfies these conditions. A lower bar is a bounded monotonic increasing left continuous function, and A upper bar is bounded monotonic decreasing left continuous function. I'm sorry, there's a wrong in this. A lower bar is less than or equal to A upper bar for all x belongs to the interval 0, 1. And we call the one cut, the one cut, as you said, that the alpha cut will be an interval. You have this alpha may be of any value. If you take one cut, you will have a single value, which we call as A0, which is the location index. Location index, the one cut, which is the location index of a fuzzy number, and A lower star we call as the left fuzziness index function. A upper star, which we call as the right fuzziness index function. Now, by using this parametric of fuzzy numbers, arithmetic operations can be defined in a simplest way. In this way, we only that location index takes the usual arithmetic operation, whereas the fuzziness index functions takes the Laplace, the lattice rule, which is the greatest lower bound and the least upper bound. Okay, and here is there are plenty of methods available for ranking fuzzy numbers. This is one such method. So as now I've told you, that this method, whenever we are having a problem which is of imprecise nature, we can go for either stochastic optimization or fuzzy optimization. For stochastic optimization, we need a little bit knowledge regarding distributive functions. What type of distributive that we have to apply for model that parameter. On the other hand, if we use the fuzzy numbers, we can model the imprecise data using fuzzy numbers. Then we call that optimization problems as fuzzy optimization. And once the problem is formulated as a fuzzy optimization problem, then we can go for the solution procedure. The solution methods are available in plenty of number, but mostly, even so far, the authors are trying to converting the fuzzy problems into equivalent Cripps forms, and then by applying the available methods, they obtain the solution easily. But the question is whether the obtained Cripps solution represents the original problem or not. That is not known. To avoid such things, it is better without converting to any classical form. Once the problem is formulated, try to solve as it is. Why they have avoided of solving the problem as it is using the fuzzy techniques is that there are a lot of drawbacks in arithmetic operations. We should try to exclude such drawbacks a little bit, all by compromises only. For example, as I said, the standard arithmetic operation does not possess the distributive property. Because of that, we are unable to develop a simplex algorithm in fuzzy version. So we have modified that operations in such a way it can satisfy the distributive property. Then it is possible to prove the theorems. Then it is possible to develop a simplex method. In a similar way, while if you consider the division, whenever you want to divide a fuzzy number by another fuzzy number, it's very difficult because the denominator fuzzy number should not contain 0. It is not always possible. If you insist the condition, then your method will not be useful for solving a variety of problems. Maybe useful to solve 1 or 2 problems. So we should exclude it. We should exclude it by that. We have done another paper, maybe in 2007, on arithmetic operations on interval numbers. Myself and Professor Veeramani. It has been published in the International Journal of Uncertainty, Fuzziness and Knowledge Dispersal System. Even if the denominator contains 0, it can be excluded to a certain extent. So it is possible to solve the problem as it is. And some of the references I have given, the first 4 or 5 references which are very much useful in developing the arithmetic operations on fuzzy numbers and interval numbers. By applying that type of arithmetic operations, we have developed simplex method in fuzzy version, and we have solved certain problems. And then by having that interval numbers, new interval arithmetic, we have done a lot of problems on system of interval linear equations, and applied in the recent years, even the 2020, we are very much interested in working in the field of again optimization problems under fuzziness. We have published certain papers of 2009, 2020 all these things, fuzzy linear programming problems, fuzzy fractional linear programming problems, fuzzy quadratic programming problems, fuzzy nonlinear programming problems. All these things we are working. I think let us conclude with this our lecture. If you have any questions, please ask me. I'm ready to answer.
Thank you, sir. Thank you for sharing your knowledge with us. The session was very informative and impressive. So we have got few questions from our participants. I will forward them to you. I will forward them to you,
Yes.
sir. Please clarify them for the participants.
Yes.
I would like to, once again, I would like to thank you, Dr.K.Ganesan, for his valuable speech, fuzzy mathematics, and I thank all the participants for their patience and attention for the. Thank you.
Thank you very much. Thank you very much for giving me an opportunity to interact with you. Thank you very much. Thank you. The answer,
Thank you, sir.
thanks to the coordinator. Thank you.